Hey everybody, this is Mr. Piercy, and in this video lesson what we're going to be looking at is how we find the area of trapezoids, rhombuses, and kites. Now one of the other things that I'm going to be doing is not just really saying here's the formula and this is how you use it, but in other videos what I've done is for triangles and parallelograms, stuff that you've been using since maybe grade school, middle school. I didn't really demonstrate how those formulas were really derived, but for these I will. Now here, the height of a trapezoid is going to be necessary when trying to find the area of a trapezoid. In fact, trapezoids are going to be something that you'll use initially to find, to approximate the area of irregularly shaped objects. So if you have something that's curving, what you'll do is you'll actually use trapezoid shapes to approximate what the area will be for things that curve initially until you learn how to find the area under a curve. But the difference between the height of a trapezoid and other objects is that with triangles and parallelograms, there's a variety of ways that we could have the base and the height. For parallelograms, remember bases can be any pair of opposite sides, any pair of parallel sides. Well, and with triangles, any side can be the base as long as you draw the height accordingly. Well, for trapezoids, uh, the bases are going to be the two parallel sides, and the non-parallel sides are legs. It's not possible for me to create the altitude or the height of a trapezoid using the legs. They can only be the perpendicular distance between whatever your two bases are. So please keep that in mind when you're trying to find the height of a trapezoid. So this is how the height of a trapezoid, I'm sorry, the area of a trapezoid formula is written. It's generally written as 1/2 times the height multiplied by the sum of the bases. Oftentimes you'll also see the area of a trapezoid as area is equal to 1/2, and then they'll say base 1 plus base 2 times the height, because remember the order that we multiply the numbers doesn't make a difference to the outcome. So sometimes you'll see it written like that as well. So where does that formula come from? So I don't want to be the kind of teacher that just says, here's the formula and this is how you use it. I want to show you, well, where does that formula come from? So here I have a trapezoid. I actually have two trapezoids. One is laying right on top of each other. So I really have two trapezoids. I have a red one and a blue one. And I just copied the figures. So and if you overlay them, you can see that they lay directly on top of each other. So the red and the blue trapezoid are congruent to each other. So what I'm going to do is I'm going to take this red trapezoid and I'm going to rotate it around its center 180 degrees and place it like that. And what we wind up with here is a parallelogram where, and let me pick a color that we can hopefully see here. Let's try black. I think we'll be able to see black. So here, let's just say this was base 1. Well, now base 1 is here. This is base 2, and so this is base 2, and of course height is the same in both of them. Well, since we know that the area of this parallelogram, it's base times height. Well, in this case, the base of the parallelogram is the sum of the two bases. So here I would adjust it to say base 1 plus base 2 multiplied by the height. And of course, because I'm only interested in the trapezoid, which would be, say, the red one or the blue one, this is the parallelogram's area. So the trapezoid is only half of that, so that's where we say it's half of base 1 plus base 2 times the height. That's where the formula came from. It is a derivation of the area of a parallelogram, but essentially it's half of whatever a parallelogram would be if we created a parallelogram out of the trapezoid that we're given. So that's how that equation came about. Now, how do we use it? Okay, so here we have a problem where they're kind of giving us a beaver created a trapezoidal shaped dam, which is, I don't know, possible, I suppose, but we'll just take a look at the area. We want to know what's the area enclosed by this particular trapezoid. Well, we want to know what are the two bases and what's the height. And they're giving us the two bases. We have a base here, we have a base here, and we have the height. So we have the information that we need to find the area. Well, substituting those things into the formula for area of a trapezoid, the height is the perpendicular distance between it, so that's the 8 radical 2. The two bases are 8 and 16, so we plug those into the equation accordingly, and then we simplify it. Well, half of 8 radical 2 would be 4 radical 2, and the sum of 16 and 8 will be 24. So we get 4 radical 2 times 24. Well, 4 times 24 would give us actually 96 radical 2 as an exact answer for the area. And I should have had a little squared here. Should have something that says squared here and squared here, but I guess I forgot that off there. So 96 radical 2 square feet is the exact answer. 135.765 rounded to 3 decimal places, so approximately about 136 square feet. Now we're going to take a look at the area of a rhombus and the area of a kite. Now, area of a rhombus and area of a kite, if you notice, have the same equation. 1/2 multiplied diagonal 1 multiplied by diagonal 2. Now, where did that come from? Well, if you recall about properties of quadrilaterals, rhombuses and kites are the two quadrilaterals where the diagonals are perpendicular to each other. Meaning that if the diagonals are perpendicular to each other, essentially what we have inside of the figures are 4 right angles. And we know the formula for how we find the area of a triangle, so we're going to use that to find the area formula of a kite or a uh, rhombus. Now, here on the left, this is a rhombus. I created it in such a way that I know this is a rhombus. Okay, so all 4 sides are the same. Let me pick a better color so it shows up against the black lines here. So here I can say, if I want to, this would be diagonal 1, and this would be diagonal 2. So this is half diagonal 1 here, and this is half diagonal 2, because remember the diagonals of a kite, the diagonals of a rhombus bisect each other. So how do I do this? Here I have 4 of those triangles in there. So I'm going to say the area is equal to 4 triangles multiplied by half of the base and the height. Okay, so simplifying here, I'm going to say 4 times 1/2, that's 2 times the base of the triangle. So the base of the triangle, we can say that's half of diagonal 1. And the height would be half of diagonal 2. Well, multiply the fractions together and the numbers, so 2 times 1/2, the 2 and 1/2, that just simplifies to be 1, so I'm left with 1/2 diagonal 1, diagonal 2 as my final answer. And that's how we derive the formula for area of a rhombus, and it works the same thing for area of a kite. That's why they have the same equations for the areas of those figures. So how do we use it? Find the area of the rhombus. Now, what we know about this particular rhombus is that the diagonals are going to bisect each other. So we know that QT and TS have to be the same, and PT and TR have to be the same. So that means that from Q to S, that has to be 16 units long, and from P to R, that has to be 22 units long. So now that we know the lengths of the diagonals, we can substitute them into the equation. So 16 for one diagonal, 22 for the other diagonal. And from there, it's just a very simple arithmetic. Use your calculator, and we get 176 centimeters squared for the area of the rhombus. So at this point, I'm going to go ahead and pause. I'm going to take a step back, and what I want you guys to do is pause the video, find the area of the two figures that we have in these diagrams. And once you have your areas, come on back, hit play, and see what your answers look compared to mine. All right, so hopefully you've taken the time to work out the equations to find the area of the respective figures. In figure 1, we have a trapezoid. So I'm going to use the area of a trapezoid figure, or formula, I should say. And anytime you use the formula, write it down. So 1/2 times the sum of the bases times the height. Substitute your numbers. So 1/2 times 7 plus 9 times 4. Well, simplifying, 1/2 times 4 is 2, and 7 plus 9 inside of the parentheses is 16. 2 times 16 gives me an area of 32 feet squared. Moving on to the next one. The next one is rhombus because it's quadrilateral that has 4 congruent sides. So I know that the diagonals that they're giving me are going to be bisected. So one diagonal is going to be 24 meters long, the other one's going to be 36 meters long. So that's how I substitute the numbers into the formula for area of a rhombus, and I wind up with 432 square meters for the answer for problem 2. Moving on, here, find the measurements of some unknown values. Now, the equations themselves for a rhombus and a kite, the equations aren't very difficult. There's really not much to do with it, but so they're upping the challenge a little bit here, upping the difficulty by, instead of giving us values for the diagonals, they're just saying that one diagonal is going to be twice as long as the other diagonal. So find the value of x. All right, well, knowing here that one diagonal is x, the other diagonal is going to be 2x. We label it that way. They give us the area of 56.25, so I substitute those into the problem here. Now, what I have here is I have 56.25 being equal to 1/2 times x times 2x. Now, on the right side of the equal sign, I can simplify the 1/2 and the 2 to just be 1, and x times x gives me x squared, so I wind up with 56.25 times x squared. The other way that I could do it is, let's say that, what if the number on the right side of the equal sign, what if it wasn't a nice number? What if it was like, instead of 2x, what if it was an odd number, 3x or 5x? If we want to avoid decimals, we certainly can. What I would wind up doing in this case is I would multiply both sides by 2 to get rid of the fraction. So we can say, here at this point, we can say or. If I multiply both sides of the equation by 2, that would give me 112.5 to be equal to 2x squared. Now, obviously, when we divide by 2, we're going to wind up back with the 56.25. We're going to wind up back up here. But sometimes getting rid of the fraction through multiplication will be easier than trying to simplify it on the right side of the equal sign. So now at this point, we're going to take the square root of both sides, and we do want the positive value only because the negative 7.5 that we would get doesn't work for the diagonals of a kite. If we were in an algebra-based math class, yes, I would want positive and negative 7.5, but I digress. Here, so the length of the one diagonal is 7.5 inches, the length of the other diagonal, 15 inches. Now, this last example that we're kind of taking a look at here, I have a little bit of an issue with it because I think it's kind of an insult to everybody's intelligence that is working it. Okay? Now, let me explain why. They very clearly state in the problem that each square represents 3 meters by 3 meters. So, and even in the diagram here, in the graph, they're showing you that each space, horizontally or vertically, they're counting by 3s. Now it's asking us to find the area of this particular trapezoid, and they're going about it in a very odd way, because personally, I would say BC, that is 1, 2, 3 spaces long. And if everything is counting by 3s, 3 spaces times 3 for each length says that this has a length of 9. And I would do that again for AD. So starting here, I have 1, 2, 3, 4, 5, 6, 7. So that means this has to be 21 spaces. And I would do the same thing for the height. Well, that seems to be the most intuitive way that I would approach this, but here they're asking us to find the absolute value difference. Now, the absolute value, this is going back way back to what we did at the very beginning of the year, known as the ruler postulate, that simply says that any length on a number line has to be positive, and the x and y axis are really just number lines that we can count in two directions on. So the distance from the x coordinates of b and c, if I subtracted one from the other, whether I said 18 minus 9 or if I said 9 minus 18, the absolute value of those differences is still just going to be 9 meters long. Okay, and for the other one, if we look at the x-coordinates of A and D, if I said 24 minus 3, or if I say 3 minus 21, either way, we still get the absolute value of 21 because we're representing a distance. It can't be negative. And the height here in this case, again, if you just counted it, that's going to be 15 meters. So I could see doing something like this, like if the trapezoid that they gave me didn't give me horizontal segments or vertical segments where I couldn't just count them, that might be a case where I would look at using the distance formula to find out how long those segments are. Or if they're not horizontal or vertical, or I can't see a reason why I would have to find the absolute value difference of it there, the way that the problem is set up. But uh, anyway, that's why I think it's not exactly, I don't know, I feel like my intelligence was insulted a little bit when they tried making me do that, because it just is so much more intuitive for us to just count to lengths. We just have to recognize we're counting by threes and not ones. But anyway, now that we know the lengths of the three values that we need, the two bases and the height, substitute them into the equation for area of a trapezoid, and this one is 225 units squared. So here, this is the last of it. Again, go ahead and just pause the video and work out these two problems, and when you're done, go ahead and hit play and see how do your answers look compared to mine. Okay, so hopefully we have you guys have your answers worked out here for these last two problems. So one diagonal of a kite is 3 times as long as the other diagonal. So this is very similar to the last one that we worked out, where the diagonals were x and 2x. Find the area of the kite. The area of the kite is 73.5. What are the lengths of the two diagonals? So the first thing I'm going to do is I'm going to find what are the values of what's the value of x. Now in this case, because 3 is the coefficient in front of one of the x's, if I say half of 3, I'm going to wind up with 1.5. And personally, I really don't care to work with fractions or decimals any more than I have to. So the first thing I did was multiplied both sides by 2 to get rid of the fraction, which gives me 147 to be equal to 3x squared. Then I divided both sides by 3, so x squared was equal to 49. Take the square root of both sides, and I get a positive or negative 7. Well, the negative 7 can't be the length of a diagonal in this case, so that's extraneous. We can't use it, so x has to be 7. So one diagonal is 7, the other one is 3 times that, 21. Find the area of the rhombus. Now here, if they gave me a graph, I could look to see what are the lengths of the diagonals or what are the lengths of sides maybe, but they didn't really give me a graph, they just kind of gave me coordinates. So all I really did when I worked this one out is I just gave myself a rough sketch of what the coordinates would be, and all I know is that I need the lengths of the diagonals, so I just did the distance formula. Now if you graphed it, it turns out that the one diagonal between M and P, because the y coordinates don't change, well, that means that we have a horizontal line. So MP is horizontal. If you graphed it, you could have just counted that it would have been 6 spaces long. Same thing with NQ. Because the x coordinates didn't change, that's going to be a vertical line. So again, if you graphed it, you could see that it was going to be a vertical line, and you could have just counted it. Otherwise, you have to use the distance formula. So the two diagonals that we got are 6 and 4. Substituting those into the formula, the area is going to be 12 units squared. So that's it in a nutshell, ladies and gentlemen, how we find how we use the area of a trapezoid to find its area. and I showed you where that formula came from. Same thing with the area of a kite and a rhombus, 1/2 times the 2 diagonals. Showed you where that formula came from and how we use it. But essentially, that's all we're looking at on this lesson. But if you have any questions about anything, ladies and gentlemen, please don't hesitate to write them down and send them to me. Come see me in class, email me your questions, whatever you need to try and get an answer, and I'll be happy to work with you and get you sorted out. Until next time, guys, thanks for watching. Take care, and we'll see you soon.